This example is looking at a decoder implementation. It's going to be done using only 3 to 8 decoders. When we're doing something like this, that we have 4 inputs, but 3 to 8 is our limitation, we're going to do a divide and conquer approach. We're going to use Shannon's expansion theory to have A times the function of what remains would be C, D, plus A naught times the function of the remaining variables. So to incorporate this, we're going to let A be our enable. To draw our diagrams for this specific component, we don't need our truth table. We have our terms that we need. So we're going to make our 2 decoders. Our decoders have our 3 inputs, A, B, and C, and they have their enable. Once we have our line decoders drawn out in our form, we'll connect in our inputs. So we have A, B, C, and D. B is going to take the role of A, C is going to take the role of B, and D is going to take the role of C when it comes to our decoder inputs, because that's the order that they're in. Then our enable is going to be driven by A. When A is 0, we want the top half to be the value that we connect. When A is 1, we want it to be the bottom half. So this spot up here is when A is 0, and this is when A is 1, allowing us to break things apart. Then, for line decoders, we've got to just OR together the terms produced from the corresponding outputs. So 0, 2, 3, and 7 are from the first half when A is 0. So we pull those. So we pull those out. For the ones that are greater than that, we'll subtract out 16 to get the value. So 12 is term 4, and 15 is term 7. And we OR them together since they're line decoders that produce min terms for those input combinations. And that produces our result.